Right, in this video, I'm going to be looking at the mean value theorem part of section 4.2. You mainly use it just to prove other theorems in calculus. What it says, though, is kind of interesting. So if you have a function that's continuous on some closed interval, differentiable on the open interval, then there's going to be some value, some number c within the interval where here we have the derivative of the function, okay, which is the instantaneous rate of change equals the slope of the line passing through the endpoints. That's this, and that's the average rate of change of the function from A to B. Okay. So that right there basically tells you what your procedure is going to be. Okay. All right, so it says there must be, so if you've got a function that's continuous on the closed interval, differentiable on the open one, there has to be a point within that interval where the tangent line to the curve at that point has the same slope as the slope of what they call the secant line through the endpoints. Okay, so look at this picture for a minute. Here's your tangent line, has the same slope as the secant line through those endpoints. Okay. So there's going to be a point somewhere in the interval where the instantaneous rate of change is the same as the average rate of change on the interval. So the idea is if you were taking a trip from here to here, okay, so maybe your trip might look something like that. If you record it, and if this was the distance, okay, and here was time, and you looked at the slope of this line, okay, you could do that to get a sense of what your average speed, your average velocity was for the whole trip. But your speed would have been sometimes faster than that, sometimes slower than that. What the mean value theorem says is that somewhere during that trip, you would have had to hit that average velocity exactly. So somewhere along that trip, at some specified point, you would have to have a line that would be the same steepness as that. It's not a max or min necessarily. It's not the highest or the lowest point. Also notice, unlike rolls, these endpoints don't wind up having to be at the same height for this to be true. Okay. All right, so the steps are there when you need them. But basically the formula tells you what you're going to need to be doing. So first you need to check for whether it's continuous and differentiable where needed. And then once you do that, you're going to calculate the derivative, and then you're going to do the slope passing through the two endpoints, and you're going to set those equal to one another. So this f of x equals x to the 6 is just a power function. So f is continuous and differentiable everywhere. Let me try that again. Is continuous and differentiable everywhere. So it'll definitely be on that interval. You need to make a statement about that. Okay, so you want to make sure it can be applied. So you now know the mean value theorem would hold true. Okay. Then what you're going to do is you're going to do f prime of x, which is the normal derivative you've been doing so much of. Okay. But then you need to do this. This is the harder part, going to be the harder part for you. Okay. So that's just the slope formula. This is like your A, and that is like your B. They're both input values. So when A equals -1, f of negative 1 would equal negative 1 to the 6, which is 1. B equaled positive 1. F of 1 would equal 1 to the 6, which also equals 1. Those do not have to be have the same value. Okay, now you're ready to do your slope. This is really just the slope. So you're going to take your f of, let me write it correctly. You're going to take your f of 1 minus your f of negative 1. Okay, that's your y2 minus y1 over your x2 minus your x1. And watch it, that's 1 minus a negative 1. So f of 1 was 1. I'll write it here, 1. F of negative 1 was also 1. Don't need the parenthesis. And the denominator is 1 plus 1, or 2. So we wind up getting 0 for that. Okay. All right, so now what you need to do is this part. Set the two equal. So now you're going to set the two equal. So 6x to the 5th would have to equal what this turned out to be. Okay. And so x to the 5th would have to be 0. X would have to be 0. And 0's in that interval from negative 1 to 1. So the c they're talking about would be 0. Okay. So this is not looking for maxes or mins. Okay, it just happened. This number right here didn't have to turn out to be a 0, and you could have still done it. Okay. So let's look at the process again. All right, so here's one where it's also a polynomial. So f is continuous and differentiable everywhere. So Rolls applies. Okay, so then I'm going to do f prime of x the usual way. Just do 4x to the 3rd minus 8. Okay, then I'm going to come over here and I'm going to think about when x equals 0, f of 0 would be 0, because 0 to the 4th, I'll go ahead and write it, minus 8 times 0 would give me 0. And when x equals 2, f of 2 would equal 2 to the 4th minus 8 times 2. Okay, and that equals 0. These do not have to equal each other. They do not have to equal 0 at this point. They could be whatever they turn out to be. Okay, now I'm going to do my slope formula, my average rate of change. F of 2 minus f of 0 over 2 minus 0. So 0 minus 0, I'm going to get 0 over 2. Okay. Now, I need to find out what causes what, for which x values, f prime of x equals the average rate of change. So I'm going to set those two things that I've got boxed equal to each other. You don't always have it equal to 0. It just happens to be on these. So one way to do this would be to add 8 and divide by 4. Okay. And then at this point, we're trying to undo something that's been cubed. So we're going to cube root. And when you cube root, you only have one of them. You don't do a plus or minus on that. And x would be the cube root of 2. Cube root of 2 would fall in between 0 and 2. So this is that c value they're talking about, cube root of 2. Okay. All right, let's try this guy. All right, so f is not continuous at x equal 1, and x equal 1 is in the interval we're looking at. Therefore, the mean value theorem doesn't apply. And we move on. Okay. All right, let's try this guy. Oh, maybe we got the same thing going on here. F is not continuous at x equal 5, but x equal 5 is outside of the interval from 1 to 4. So f is continuous on the interval. Okay. Now we need to look at differentiability. So let's do the formula for the first derivative. So it's a quotient rule problem. So I'm going to do 1 times x minus 5 minus the derivative of the bottom, which is also 1, times the top as is, over x minus 5 squared. So this will be x minus 5 minus x. So I'm going to get a negative 5 on top with x minus 5 squared on the bottom. So again, it's not differentiable when x is 5, but that's outside the interval. So f prime is continuous on the interval, open interval from 1 to 4. Okay. All right, so now we're going to wind up taking this and set it equal to what we get when we do the average rate of change, the slope of the points at the endpoints of those intervals. So x equal 1 corresponds to a y value of 1 over negative 4 or negative 1/4. Okay? And when x equals 4, the value of the function at 4 turns out to be 4 over 4 minus 5, which is 4 over negative 1 or negative 4. So let me double check those two. Yeah, good so far. Okay, so then f of 4 minus f of 1 over 4 minus 1. Okay, so that would be negative 4 minus a negative 1/4 over 3. Okay, so that's negative 4 plus 1/4 over 3. Right, let me get rid of that little fraction by multiplying the top and bottom by 4. I'll get negative 16 plus 1 over 12. That's negative 15 over 12. And that's divisible by 3 top and bottom, so I can simplify that and get negative 5/4. Okay. All right, now I'm going to try to see if I can get some more paper. All right, so that's not the C value. That's just the average rate of change. There we go. That's just the average rate of change from the point 1 negative 1/4 to 4 negative 4, okay, which I got from using the x of 1 and x of 4 and just doing the normal slope formula. Okay, so now what I need to do is I need to take and find out what causes this, the formula for the derivative, to equal the average rate of change. All right, so you may or may not have noticed, but do you notice the numerators are both negative 5? For these two fractions to be equal, that has to equal that. Okay. If you didn't notice that and you're just thinking about the normal way you solve proportions, you might have cross multiplied. So if you did that, you'd wind up thinking or seeing that negative 20 would wind up equaling negative 5 times the quantity x minus 5 squared. Okay. So let me divide both sides by that negative 5 there. And so I'd wind up with x minus 5 squared equaling 4. Like, I really knew that already, but I just didn't think it would be something that you would naturally realize. Okay. Now, once you get to there, you have to undo that. So good way to undo that is to square root. But when you do square root, don't forget the plus or minus. Okay. So x minus 5 might be 4, or x minus 5 could equal negative 4. All right. Then you can finish it up from there. So you're going to add 5 and get 9. Here you're going to add 5 and get positive 1. All right. Now, oh, wait. Sorry. What made me realize I did something wrong is neither one of these is within the interval. And then it hit me that I never took the square root. So go back and think of that as a as a 2 and a negative 2. That explains it. Because mean value theorem would guarantee that there's a number in that interval, and I didn't get one in the interval. So that's how I caught the fact that the square root of 4, I didn't do it. I should have had 2 and negative 2 here. So make sure you fix that. All right, if I add 5, I'd get 7. Here, if I add 5, I'd get 3. Now, 7 is not the C value that is guaranteed by the mean value theorem. It's outside of the interval. But 3 is inside the interval. So C would be 3. Okay. And I think it has to be inside the open interval, okay, which it is. So C would be 3. Okay. One last one I just wanted to look at is this guy right here. On this one, mean value theorem is not going to apply, but I just wanted to come up with an example with one of those sharp points. And here's a case where it can happen. So you probably know already that the absolute value of x is a v-shaped thing with one of those sharp points. So you know how if we did limit from the left and the limit from the right, how they don't wind up, or that let me say it better, the limit exists, that the slope of this piece right here would be 1, but the slope would be negative 1, but the slope of this piece right here would be positive 1. So when you're looking at this spot, this sharp point right here, you can't even imagine a tangent line really touching it. So it's not differentiable at that sharp point. Okay. So this is going to have that situation. And where that's going to happen is right there. So it's not differentiable. It's continuous, but it's not differentiable. Where 2x plus 1 would equal 0, which is at negative 1/2. And negative 1/2 is in that interval, so MVT doesn't apply. Okay. All right, so I wouldn't expect you off the top of your head to recognize what the issue was there, but just wanted to have another case, another situation where the mean value theorem wouldn't apply, and that's one that I thought would be good to use. So it doesn't apply because absolute value has one of those sharp points, right? And right there, it's not differentiable, okay? All right, that's it.